I'd like to talk about some side chain reactions, and both of these side chain reactions are considered to be radical processes. That is, they're processes that are based on movements of single electrons. Both of these depend upon the presence of a benzylic hydrogen. Now, a benzylic hydrogen, I'll show you over here, is a hydrogen connected to the carbon connected to the aromatic ring. When this hydrogen is removed to leave a single electron on this C, this single electron is subject to resonance. That is, it can move around the aromatic ring because of where it is. Now, if the radical had been present on the ring originally, then this kind of resonance would not be possible. But since the original radical is connected off the ring, then we can get this kind of movement where the dot can be here, 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 and here. Now, first of all, looking at the KMNO4, this is an oxidation reaction. It's a radical oxidation. As long as we have a benzylic hydrogen attached to this carbon here, it doesn't matter what this chain looks like. It could be 10, 15 carbons long. It doesn't matter. It's always going to give this as a product. This is benzoic acid. Now, the reason for this is because at some point during the mechanism, we get this radical as a this stabilized radical as a intermediate, and what happens is that eventually this stabilized radical will break down everything around it, and we'll end up getting the benzoic acid as a product. So even if radicals form out here on the chain, those will decompose very quickly because this is the only stable radical that will be present. The other process that I want to talk about is N-bromosuccinimide. That's NBS, N-bromosuccinimide. And that compound is this one here. Now, this compound is subject to becoming a radical because when it's subject to heat, this N-Br bond can break and we get Br dot and N dot. Now, what can happen then is that the N dot can remove the benzylic hydrogen and form this stabilized radical that I was alluding to earlier. The Br dot then can react with this stabilized radical to put a bromine group on the benzylic position. And that's what the NBS will do. It will only ever attack the C that is directly attached to the aromatic ring. And any product we come up with will have a Br connected to the benzylic position. It doesn't matter what these other groups are. Alright, let me show you a couple of examples. Alright, so let's say we have something like this. And I attack it with KMNO4 for the reasons I talked about earlier. The only product we get will be this one, and of course that's due to the stabilized nature of the radical we get attached to that carbon atom. So that's the only product we get from that. If I take the same product and I treat it with N-bromosuccinimide, NBS, the product I get is this. Now I know there's a lot of carbons and hydrogens here, but the only one that matters is the benzylic carbon, and the benzylic carbon will lose one of its hydrogens and be replaced with a Br. Let me point out that if we don't have any hydrogens on the benzylic carbon, there will be no reaction. So something like this with NBS, no reaction.